In today's lecture, we're going to focus on Chapter 2, called the metric system. The metric system has basic units, and we are going to add prefixes to these units. So we're going to see meter, gram, liter, and second, and then we can add prefixes such as kilo, micro, mega, giga, and we'll get to those as we go through here. So you are responsible for knowing the prefixes that are red and blue here. So centi, milli, micro, nano, pico, kilo, mega, giga, and tera. Please pay attention to the symbol because some are uppercase and some are lowercase. And we will be using these in our metric conversions in this chapter and throughout the rest of the semester. So I have created kind of a document to help us visualize the order of units here. So when I say base, which I put the star, an example of a base could be any of those we just said, could be grams, it could be meters, could be liters, and any of those could be something that we put a prefix in front of. So anything above the star here is larger than the base, and anything below is smaller than the base. Okay, so for example, deca, there is, if we're looking at meters in all of these, 1 decameter is equal to 10 meters. 1 kilometer is equal to 1,000 meters, and again, you may prefer to write that as 10 to the third, which is fine. 1 megameter, so make sure when you see mega, it is a capital M. That is a million. You can also write that as 1 times 10 to the 6th. And then giga has 1 billion meters in it. And I do believe it's easier to write 1 times 10 to the 9th. And then we have tera, which is 1 times 10 to the 12th. Save ourselves some time there with the zeros. Okay. And again, this meter word could be replaced with gram or liters or seconds as well. So things that are less than or lower, smaller than the base is deci, centi, milli. We're going to label this one micro, which I know is a little bit different. This is a fancy U. We call that a mu. And so we're going to go ahead and look at deci. There are 10 decimeters in 1 meter. There are 100 centimeters in a meter. There are 1,000 millimeters in a meter. There is a million or 10 to the 6th micrometers or micrometers in a meter. There is 1 billion nanometers in a meter. And again, sometimes it's easier to write 1 times 10 to the 9th. I think it is in the calculator. And then there is 1 times 10 to the 12th picometers in a meter. So you will be responsible for knowing all of these on here. Okay. Now, what are we going to use these for? We are going to use these values as what we call a unit factor or a ratio. So you can put the number on the top or the bottom as long as what we're going to see as we go on here, as long as the units cancel. Okay, so if we know 1 meter is equal to 100 centimeters, we can flip this ratio in whatever regard we need when we put it into the mathematical equation that we're going to be doing on the next couple of slides. So the method we're going to be using in chemistry is called dimensional analysis. Dimensional analysis is also known as the factor label method, and this is the way you have to do problems in this class. So I like to help you understand by using the metric system so that when we get to more complicated chemistry math concepts such as the mole, the setup is not completely brand new to you. Okay, so when you're working with dimensional analysis, you always start with your initial unit, and your unit goes down at the bottom, and your desired unit goes on the top here. Okay, and I'm going to be doing multiple steps here and multiple examples as we go through this. So you're going to see some examples here as you go through. But again, the big thing is you have to memorize the conversion factors to be able to perform dimensional analysis. So here is our first example with dimensional analysis. This is considered a one-step problem. What is the mass in grams of a 325 milligram aspirin tablet? So when we start with a dimensional analysis problem, we always want to write what we're starting with. We do a multiplication sign, and then the unit you start with immediately goes and gets placed on the bottom of the first fraction bar. And the unit you are going to, which is the one you want to finish in, which is grams, goes on the top. Once you have the units in, you place the numbers. So units first, numbers second. So in 1 gram, there are 1,000 milligrams. Now, when you have a number on the bottom of the fraction bar, you divide by it. So the math for this in your calculator would be 325 divided by 1,000, which gets you 0.325 grams. Okay? I'm going to show you a couple other examples here. So let's say we are starting with 500,001. And that is micrometers. So again, that unit of micrometers goes immediately on the bottom. Whatever you start with goes on the bottom. What you're going to goes on the top. Then you fill in your numbers. So if you go back on the chart, in 1 meter, there is 1 times 10 to the 6th, or you're welcome to write 1 million down at the bottom there. So what we're going to do, we're going to take 5,001, and because this number is on the bottom, we're going to divide. So my answer when I divide this is 0.500001. Okay? And again, remember, you're always welcome to use a calculator in this class. And our unit, to finish this off, all answers require a unit is the unit that is on the top. Okay? Let's do another example, 875 kilograms. So the unit we start with goes on the bottom. The unit we're going to goes on the top. We consider these one-step problems. I'm going to go ahead and fill in my numbers. 1 kilogram contains 1,000 grams. Now this is a little bit different. This is on the top. So therefore, we can see that we take 875 and we're going to multiply that because it's on the top of the fraction bar by 1,000. And therefore, my answer ends up being 875,000 grams, because you always want to use the unit that it's on the top. Okay? I'll do one more example here. We have 9,400, and I put that decimal point to indicate that those zeros are significant. Liters, put liters, and then remember this big M is mega liters. I wanted to remind you of that. If it is a little m, it's milli, but a big M is mega. So in 1 megaliter, there are 1 million liters. Okay, so again, I'm going to divide this answer. And so my answer ends up being 0.009400. And again, my unit is what I end with, which is megaliters. So I took the number and divided it because this number was on the bottom. Now again, you could have multiplied by 1 and divided by a million. I just skipped the 1 part because that is itself. Now we're going to make this a little more difficult and do 2 steps, which is what we're more going to see. So a 2-step problem involves going from a metric prefix like deciliters and ending in another what we call prefix because it has something in front unit. So this is going to be 2 steps, so let me demonstrate. So we're going to start with 125 deciliters. Now, when we do this, we again start with what we're given, put it on the bottom, and what we're going to do is go to the base. The base is the unit that is the same between both prefixes. So both of these contain liters, so we're going to go to what we call an intermediate, which is the base unit without a prefix. All right, so in 1 liter, we have 10 deciliters. Now, we do not solve. This is the beauty of dimensional analysis. We keep going. So we have canceled out deciliters because it's on the top and the bottom. We have liters. We put liters on the bottom. And we're going to finish off in what we are trying to end in, which is milliliters. And in 1,000 milliliters, there is 1 liter. Now, how to do the math here? If I were you, I'd take 125. You could multiply by 1 if you wanted. I do skip that. You could multiply by 1,000 and get an answer. And then you could divide by 10 here and get an answer. Try that. Or you could take 125 divided by 10 because that's the first fraction bar, get an answer, multiply by 1,000. So again, we are multiplying by anything on the top and we are dividing by any numbers on the bottom. Okay, so do that on your own and make sure you're getting the same answer I am. So I got 12,500 milliliters. So that is a two-step problem because you have to stop at the intermediate, which in this case was liters. Go ahead and do one more example here. So 7.35 times 10 to the 22nd kilograms. So we're going from kilograms to nanograms. So our base here, which is the unit without the prefix, is going to be grams. So I'm going to go from kilograms to grams. There is 1,000 grams in a kilogram. And then I'm going to do a second step because I still have to get to nanograms. And grams is on the top, grams goes on the bottom. What you're ending up in always needs to end up on the top. So in 1 gram, there is 1 times 10 to the 9th nanogram. You're welcome to write that as a billion as well. I just find that to be a little bit easier. Now, you will have to figure out how to put this number into your calculator. If you have a calculator similar to mine, you want to type 7.35 and then you want to find the E key. It has to be a capital E, not a lowercase e. So on mine, I hit the second button first up in the corner, then I hit the E key, and then I would type 22nd. You may Google that using your calculator type to see how to put in exponents on your calculator. So please reach out to me in class or after class if you're having trouble with how to use your calculator, because this is something we're going to be using a lot. So since these are all on the top, I'm going to be multiplying this number by 1,000 and by 10 to the 9th, and my answer ends up being 7.35 times 10 to the 34th. I'm going to put my units down here, nanograms. Okay, so try that on your own. All right, moving on. We are also going to be doing English conversions occasionally. You do not have to memorize English conversions. I am providing you with the conversion factor shown below. If the problem involves another conversion factor that's not on this chart, I will provide it for you. This is on your equation page in your recitation packet. So let's do a couple examples here. The idea is still the same, using the unit canceling or dimensional analysis method. So the length of the field is 120 yards. What is the length in meters? So when we do this, we're going to go ahead and do that same process where we go ahead and do yards. And we want to get to meters, so I'm going to go ahead up and look on my conversion factors, and I see that I have a yard to meter conversion. So 1 meter is 1.0936 yards. Let me go ahead and plug that into my calculator. So what I'm going to be doing is 120, and then I'm going to divide by 1.0936. And my answer ends up being 109.73. Now to round that to significant figures, because we want to keep that in mind, this number right here has 2 sig figs. So I'm going to round this answer to 2 sig figs. So that ends up actually getting me 110 meters without a decimal point at the end there. Okay. You always want to base your significant figures off the number that you start with. Let's do another example here. A container holds 15.4 pints of liquid. How many milliliters is this? So using those conversion factors on your equation page or in the previous slide, I'm going to go ahead and do pints, and I'm going to go to quarts. Again, all I'm doing is getting this information from the conversion chart. So we're trying to get closer to milliliters. I am then in quarts. Again, anything that you have at the top goes on the bottom to cancel it out. And I can go to liters. That conversion factor is given to me. And then I'm going to go ahead and go from liters to milliliters. And that is one that you do have to know because that is a metric conversion. Now to do the math for this, I'd take 15.4. I would multiply by 1. I would skip that, but you could still do it. I'd multiply by 0.946. And I'd multiply by 1,000 and I'd get an answer. Then I would divide by 2. So please try these on your own to make sure you're getting the correct answer. When I get this answer, I get 7,284.2. And then I'm going to round. So the provided number has 3 sig figs. So I'm going to go ahead and round this to 3 sig figs and round that to 7,280. And my unit is milliliters here. Okay? So you can always write the original answer and then round to your sig figs. All right, so now we are going to look at compound units. A compound unit is something that has a numerator and a denominator unit. So we're going to do our first practice problem with that. We're going to go from 55 miles an hour to meters per second. I want to remind you that that per word means division. So when I write this, making sure that I write 55 miles per hour. So I am showing the miles in the numerator, hour in the denominator is very important. Now, this is a tedious step-by-step process, so I'm actually going to give us one extra conversion factor to save some time, and I would provide you with this if it saved us some time. So 1 mile is actually 1,760 yards, so I'm going to add that to our conversion factors to save a couple steps. So when you work with this, the miles is going to be converted to meters and the hour is going to be converted to seconds, but you have to do it in 2 separate portions. So I'm going to first focus on miles and leave this hour at the bottom and ignore it. So I'm going to go ahead and put miles on the bottom to cancel it out, and I'm going to go to yards. I'm going to use that factor I just gave you. And then I'm going to go right ahead and go from yards to meters, which is provided on your conversion chart. So 1 meter is 1.0936 yards. Now, I have successfully gone from miles to yards, or yes, miles to yards to then meters. So I'm done with the top, but now I need to focus on the bottom, and this is the new step. So remember, 55 miles an hour is the same as 55 miles per 1 hour. Since hours is on the bottom here, to cancel the unit, you have to put it in the opposite spot, which is on the top. That is what makes these difficult. So hour goes on the top to cancel it out, and then we need to get to second. So I'm going to go to minute first. So 1 hour is 60 minutes. And then I'm going to go ahead and cancel out minute again by putting it on the top and finishing it with second on the bottom. 1 minute has 60 seconds. Okay? So now we do not do the calculations in between. We write this all out and then we do it. So let me show you how I do it. I take the calculator. I do 55 times 1760. You could times by 1, times by 1, times by 1, but I'd probably skip those steps. Get an answer. Divide by 1.0936. Get an answer. Divide again by 60. Get an answer. Divide by 60 again. Okay, now there are many other ways to solve these problems. So as long as you're getting a similar answer to me, then you're probably doing it the correct way. But there are many other ways. As long as your setup looks like this and your answer matches, you should be fine. The answer I'm getting is 24.587. And that is not in significant figures. So if I were to round that to significant figures, that would be 25. And then my unit is what is not canceled out, which is meters per second. Okay? Make sure you write meters with an M. It is not MI or ME. So that is a double unit conversion problem. We're going to do one more example here. So we're starting with 105 kilometers per hour. Please making sure that you write so that probably should have been an R there. The kilometers in the numerator and the hour in the denominator. So the kilometer is becoming meters and the hour is becoming seconds. So let's focus on one at a time. So kilometers is going to go on the bottom. Meters is going to go on the top. And this is metric. So you are expected to know this conversion. So that was an easy conversion. Now again, hours is on the bottom. I need to put hours on the top to cancel that unit out. I'm going to go ahead to minute. Now, you may know the hours to second conversion off the top of your head, and you are welcome to do that. I'm just going to go ahead and do the way that most people end up doing. Okay? Now, how I would do the math, I'd take 105 times 1,000, get an answer, divide by 60, get an answer, divide by 60. Okay? Again, many other ways to do this. When I do that math, my answer ends up being 29.2 and that is meters per second. Okay. Now, sometimes we're working with squared or cube root metric conversion, so I'm going to show you how to solve those. So we're going to go ahead and start with 5.8 centimeters squared. Now, we're trying to get from centimeters to meters squared. So what you have to do here is first focus just on the centimeters to meters, which is a normal metric conversion. There's 100 centimeters in a meter. But to cancel out this 2 here, what we have to do is actually add parentheses and square this entire conversion factor. When you do that, you square everything, the numbers and the units. Now, 1 squared is 1. Meter squared ends up being the answer we want, which is good. But you do have to square the 100 before you end up doing it in the math problem. So when you square 100, you end up getting 1,000. So you kind of need to think about your problem now being 5.8 divided by 1,000 because you squared the 100. All right, so I like to actually write it under here. It doesn't look the best, but it helps you remember what you need to do. So when I do that, my answer ends up being 0.00058, okay, meters squared. So you cannot just go from one to the other. You need to take into account that square or cube root. So I'm going to go ahead and do one more example here. So we're starting with 0.0251 liters cubed. So I'm going to go ahead and do a liters to milliliters. There's 1,000 milliliters in 1 liter. But to cancel out this 3 here, we need to cube root everything. You don't have to draw these arrows. I'm just showing you that it does go to everything. The only thing it really affects is that 1,000. If I cube the 1,000, it actually ends up being 1 times 10 to the 9th. So I'm really going to take 0.00251 times 1 times 10 to the 9th. And my answer ends up being for that 2.51 times 10 to the 6th. Now, your answer may give it to you in scientific notation, or it may give it to you in a big number form. I don't care if it's in scientific notation or not. I think it's easier to be in scientific notation, but you do whatever works for you, as long as you are showing your work and have the correct answer. We're going to quickly talk about percentages. When we're working with percentages, you have to remember that you have a total sample amount on the bottom, the quantity that you're talking about on the top, and then you multiply by 100. The only issue with this is you're not multiplying by 100 and then putting the percent sign in there. That is sometimes shown that way, but truly you do not actually put the percent sign. So you're just going to multiply by 100. So let me show you an example here. Let's say you have bronze, and bronze is actually an alloy, which is a mix of metals. It contains copper and tin. If we have a sample of bronze and it has 79.2 grams of copper and 10.8 grams of tin, what is the percent of copper? So again, the thing on the top is what you're focusing on, which we are talking about copper. And the bottom is the total. So the total is the 79.2 plus the 10.8. So I'd solve this bottom number first, then I would divide, and then we're going to multiply it by just 100, and your answer ends up being 88% copper. Okay. Now, if you were to find the other percent, you could then, remember percents are out of 100, you could do 100 minus 88% to get your percent of tin, okay? And that would get you 12% tin, in case the question asked that. Now remember, percents are always out of 100 parts, so when we say 25%, you can also keep in mind that that is the same as writing 25 over 100, just as 10% is the same as writing 10 over 100. So sometimes if we see or say that something is 4.70%, we can say that it is 4.70 of that part that we're looking at over the entire 100 of the sample. Okay, so sometimes we're going to be doing that in class or during a lab. So percent unit, you can use percents as a conversion factor here. So if we have 4.70% iron, what is the mass of iron in a sample weighing 92 grams? So if we start with our 92 gram sample and we have 4.70%, we can go ahead and put our sample on the bottom and the grams of the iron on the top. Well, that percent here can be then written as 4.70 over 100. So to do this math, we'd take 92 times 4.70 divided by 100 and get 4.3 grams of iron. Now we're going to be doing some volume calculations. You are expected to know the calculation for the volume of a cube. It is length times width times height. A quick little note there, when you are calculating volume, you need it to be in the same unit. So in this case, the volume of this object is centimeters by centimeters by centimeters. You could not have centimeters, centimeters, and meters. You'd have to make sure they are all in the same unit. When you are multiplying the numbers, you are also multiplying the units. So oftentimes volume is in this class, centimeters cubed or cubic centimeters. Now, I did show you an example here above this, but this is another way to do it. Let's say you have 498 centimeters cubed, and you'd like that in inches cubed, okay? You could, how I taught it to you was to do 498 centimeters cubed, and then to go ahead and do a centimeters to inches conversion, fill that in, and then cube root the entire thing. But you can see here that they actually just did the problem 3 times. It is up to you what you prefer. I really am fine with either, but the thing is with this method they're showing you here, you need to show it 3 times, where for me, when you're showing it my way, you just have to remember that you are cubing everything inside here. So you're going to cube that 2.54 before you divide. Okay, so try it whichever way you like and make sure you get this answer. Now, volume by displacement, whenever we have an object that has a weird shape that you can't just measure the length, the width, and the height, there is a very simple way to calculate its volume, and it is called water displacement. So you have an amount of water in, let's say, a graduated cylinder here, and you indicate the initial measurement. You add the object and see how much the water level changed, and how much that water level changed is actually your volume, usually in milliliters, for that object. And we're going to be doing that in lab at some point. So for example, if we have an irregular shaped piece of jade here, and we started at 50 milliliters, we added the piece of jade, and it now is at 60.5. We can subtract our 60.5 minus our 50.5, and we can get, oh, excuse me, it's actually just 50 here. Let me rewrite that. 60.5 minus our 50, and we can see that our volume of our jade object is 10.5 milliliters. Okay, so it works well for irregularly shaped objects because you can't measure them as easily as you could, such as a cube. All right, one of the last concepts we're going to focus on in this chapter is density. You will be given this equation. Density is mass over volume. You're going to see it written like this. Density equals mass over volume. Typical units for density is mass, which is always going to be 99% of the time going to be in grams, which we're going to use a G for. And then volume, which there's 2 options. Either milliliters is more typical or centimeters cubed. Now, a good piece of information is 1 milliliter is equal to 1 centimeter cubed, so they have a equal relationship. Now, occasionally we do have a grams per liter conversion, and that is for gases, but we will really not focus on that in this course. So keep in mind when you're looking at something, its density, if it sinks in another object, then the object is denser. So if the object sinks, it is denser than what it is in. If the object floats, it is less dense than what it is in. So you can use kind of a graduated cylinder method to just, without actual numbers, to see which one is more or less dense here. Obviously, out of this graduated cylinder, S3 is the densest object, and L1 is the lightest or the least dense liquid. Okay, let's do a couple calculations for density here. So what is the density? I'm again going to give you this equation of a platinum nugget. It has this mass. I like to always indicate the variable, and it has this. So you're going to need to know that centimeters cubed is volume. So let's go ahead and plug that into our equation. I like to rewrite my equation and then plug it in. So 224.5 actually we don't need this 0 here, grams over 10.0 centimeters cubed. And when we go ahead and divide that, check my answer here. When we divide that, we are going to get 24.45. And our unit is actually the division of the units here, grams per centimeter cubed. Now, we want to round this to 3 sig figs because you're only as good as your weakest player, which means you're only going to have a sig fig that is as low as your smallest amount. This has 3 sig figs. This one has 4. So I'm actually going to round this answer to 3 sig figs. I'm going to go ahead and round this to 24.5 grams per centimeter cubed. Sorry, I had to put that in there kind of small. So I like to get my answer and then round. Let's do one more example here. What is the volume? So we're looking for V. And we have a mass of this and a density of this. So I'm going to go ahead and set that up. Density equals mass over volume. My density is 2.31 grams per centimeter cubed. My mass is 7.85 grams. And my volume, I like to leave it as a V. Now, I did this example specifically because it probably has been a while since you have solved for variables on the bottom. So you can go ahead and I just want to remind you to solve. When you have a variable on the bottom, you can multiply both sides by that variable to get it to be on the top of the numerator bar. So I'm going to go ahead and rewrite that then as V times 2.31 equals 7.85 grams. So by multiplying that, we canceled out these volumes. And now what I'm going to do is, in another color, divide both sides by 2.31. So basic algebra skills is very important in this course, so I try to really walk you through all these steps as much as I can. So then in your calculator, you're going to go ahead and do 7.85 divided by 2.31. And when I round that to sig figs, I'm going to get 3.40. Since this is volume and my density is in centimeters cubed, my answer is in centimeters cubed as well. Okay? So we can also use it as a conversion factor. I'm going to go ahead and show you how to do that. So we have an automobile battery containing 1,275 milliliters of acid, and they give us a density. How many grams? So there's a couple ways to solve this. I will show you both ways. You can go ahead and start with what you're given. 1,275 milliliters. And similar to dimensional analysis, if you have milliliters on the bottom, you can go ahead and put that to cancel it, and you can put grams on the top. And then you can use this factor to fill in. So the 1.85 goes wherever the grams are, or excuse me, 1.84. And then remember, per milliliter is the same as 1. So you can actually just multiply these numbers to go ahead and get your answer in grams. So when I multiply those, I do that right now in my calculator, 1,275 times 1.84, I get 2,346 grams, okay? Another way you could do this is you could use the equation density equals mass over volume. If you're given your density as 1.84 grams per milliliter, my mass is 1.84, and I'm trying to find, forget that I said that. I put it in the wrong spot. We are trying to find our mass. I'm going to go ahead and put an M here, and I'm going to use my volume and fill in my volume. So again, this is just a different way to do the same problem. You decide which method you like, 1 or 2. So you could then multiply both sides by 1,275 and get the same answer of 2,346 grams. So 2 ways to do it. Use it as a conversion factor in way 1, or use the density equation in way 2. But either way, you get the same answer. All right, and to finish this off here, really, we're going to look at temperature. In chemistry, or in the world, there are 3 temperature scales: Fahrenheit, which we are familiar with; Celsius, which is more of a European method; and then Kelvin, which is the science one we're going to be using. Kelvin was created because it is an absolute temperature scale, meaning there is no zero, or there is no negative numbers. It ends at 0. So, which is very handy, because putting a negative in regards to Fahrenheit or Celsius can really screw up a calculation. Hopefully you are well aware that on the Fahrenheit scale, water freezes at 32 and water boils at 212. You will need to know that on the Celsius scale, water freezes at 0 and water boils at 100. You do not have to memorize this, but it is interesting. Water freezes at 273 and water boils at 373. So you do not need to know the Kelvin, but you do need to know the 0 and boiling temperatures, freezing and boiling temperatures of Fahrenheit and Celsius. So these are your equations you're going to be provided here. You're going to be provided this on your equation page, the Fahrenheit and the Celsius, and then the Kelvin and Celsius equation. You just have to know how to utilize them. So I'm going to go ahead and do an example here. If our body temperature is 98.6 Fahrenheit, what is that in Celsius and what is that in Kelvin? So I'm going to go ahead and do two separate problems here. So I'm been given Fahrenheit. I'm going to replace that into where the F is. So 98.6 equals 1.8 times degrees C plus 32. So to solve this, I want to get this C by itself, so I'm going to go ahead and subtract 32 from both sides. This then gets rid of this. And I go ahead and subtract 32 from the 98. I get 66.6. I'm going to go ahead and bring down that 1.8 times degrees Celsius. Now, to get the variable by itself, you have to do the opposite operation. So I'm going to go ahead and divide both sides by 1.8. These cancel out, so I'm left with just 37 degrees Celsius, okay? So 98.6 degrees Fahrenheit is 37 degrees Celsius, and then we want to go ahead and utilize this and place that into this equation. So we're going to go ahead and do Kelvin equals degrees Celsius plus 273.15. Again, you do not have to memorize these equations, you just have to know how to utilize them. 37 plus 273.15. So that's a pretty simple one. You just go ahead and add those. And the answer in Kelvin is 310.15. Kelvin actually does not have a little degree symbol because it is an absolute, just a small thing. So I just wanted to point that out. We're going to be talking and calculating heat. So heat is actually a measure of the total energy, where temperature, and we do use these terms interchangeably, especially in our world, but heat and temperature are two different things. Temperature is the measure of the average energy, or we're going to learn average kinetic energy, or the energy of movement. So if you have the temperature of your house, it's actually measuring the movement of the molecules in your house. Now, heat is in two units, the joule, which is a capital J, or calories, and that is similar to food calories, and we will talk about that at a later date. So when we're looking at heat versus temperature, we want to understand that both beakers are at 100 degrees Celsius, okay? But this one, letter B, has twice the amount of heat because it has twice the amount of water. So their temperatures are the same, but this one has more heat because it has more water, which can hold that temperature. So we're going to focus a lot on that in a later chapter, but it is just being introduced to you as heat and the term temperature.